Hi, everyone. Welcome back to Innovations in Catalysis to Address Modern Challenges, a workshop of the National Academies of Sciences, Engineering, and Medicine. This workshop, hosted by the Chemical Sciences Roundtable, seeks to explore how the chemistry and chemical engineering communities can contribute practical solutions to improving the production of chemicals through innovations in catalysis. My name is Chris Bradley. I'm a program manager in catalysis science in the Chemical Sciences, Geosciences, and Biosciences Division at the U.S. Department of Energy. And I'm one of the planning committee members and also your moderator for this first session. So to give you a brief recap from yesterday, we heard from 3 keynotes and also moved through 2 sessions of presentations. The keynotes all focused on some aspect of chemical sustainability, as David Berkowitz provided us an update on momentum building with the Federal Interagency Sustainability Report. Susanna Scott shared views from academics on emerging areas, including polymer and plastics upcycling. And Bob Mahon provided an industry perspective on the need to consider the complexity of chemical processes, involving not only catalyst development, but the role of process and systems level integration. Beyond the keynotes, we heard several excellent talks from chemists and chemical engineers on forefront topics, including biocatalysis, integrated catalysis, emerging strategies in organic synthesis, mechanochemistry, and mechanocatalysis, as well as insights on the future of decarbonizing commodity chemical streams. Today begins the second day of the 1.5-day workshop, and it's going to feature 2 sessions. This first one, titled Carbon and Other Resources for the Future, will highlight 2 speaker presentations. The second session of the day is a special one called Vistas in Catalysis. The Vistas in Catalysis session will feature 15 rapid-fire presentations by researchers across multiple career levels, and it will allow them to share emerging results on new catalyst discoveries, novel applications of catalysis, and new techniques for understanding catalytic mechanisms. Just as some reminders, once we get to the Q&A and discussion period, if you have a question and you're physically in the room with us, please line up behind the microphone stand and I'll let you know when it's your turn to speak. Alternatively, if you're unable to come to the mic, you can raise your hand and someone will bring a floating mic over to you. For those with us virtually, please just remember to use first the raise hand feature on Zoom to indicate you have a question for the speaker. I'll let you know when it's your turn, and then you'll, at that point, be able to unmute yourself. So with that out of the way, I'd first like to introduce the initial speaker for session 3, Professor LaShonda Corley. She is a distinguished professor in the departments of materials science and engineering, and also chemical and biomolecular engineering at the University of Delaware. Her research interests include functional polymeric material design, bio-inspired systems, hierarchical peptide polymer hybrids, as well as sustainable materials. She's received numerous awards, but I will highlight her recent election as a fellow of the American Physical Society this year. LaShonda is also involved in many collaborative research efforts, and since I'm at DOE, I'll just shamelessly plug her as the director of the Energy Frontier Research Center, or EFRC, at Delaware in the plastics space, called the Center for Plastics Innovation, or CPI. I'm sure she's going to obviously mention that during the talk. So without further ado, let's all welcome LaShonda virtually. She tells us about plastics as a chemical feedstock.
Good morning, everyone. I'm delighted to be here today. LaShonda Corley. And so I'll first, let me get my slides primed. Okay, wonderful. So today I want to share with you some thoughts about how we can reimagine plastics waste as a valuable feedstock. So plastics waste, of course, is a global challenge that has significant consequences. However, plastics will continue to serve toward societal advancement. Plastics are used in many applications due to the diversity of approaches that can be achieved via chemical and manufacturing. For example, plastics have a high strength to weight ratio, which are ideal for the transportation sector. This leads to safer vehicles that weigh less, reduce energy demands, and harmful emissions compared to older technology. The barrier properties and chemical resistance of plastics enables food security and therapeutic access. By protecting food, drink, and medicine from moisture, air, and light, plastics packaging enables fresh food and therapeutics to be transported and stored globally, improving shelf stability. The insulating nature of plastics is also a major contributor to reducing pollution through a reduction in residential and industrial energy demands. Processability of plastics via varied techniques allows us to shape and form different products, even on demand, so we can tackle numerous technological problems. Yet we still have a steady accumulation of these beneficial plastics throughout our environment, and this impacts our natural resources as well as human health and has emerging equity issues. So when we think about this, we can start to think about the benefits of plastics. Plastics use is not really the main source of the problem. The production of common plastics generates environmental pollutants and green gases and consumes a lot of energy due to the conversion of plastic production. So plastics use is part of the whole landscape of how we think about this. During use, the major drawback of plastics is the potential for migration of additives or other micro and nanoplastics into the environment, which ultimately can impact the human body. Once plastics are discarded, additional challenges are involved, such as accumulation of plastics in landfills. Yet plastics waste don't always have to be considered a problem. We have to figure out a way that we can balance and live with this from a societal benefit standpoint. They represent a potential feedstock that can generate a new source of thinking about plastics at their end of life. To address plastics waste toward a circular framework, there are numerous pathways that have been developed as alternatives or supplements to discarding plastics waste or even incineration. For example, deconstruction of plastic products into smaller building blocks can be used as feedstocks for new plastics, as shown in this diagram in a recent review article from CPI researchers. You can even take potentially the same material or direct to other markets as chemical feedstocks, such as lubricants and adhesives. It is essential to redesign our processes to connect the links between plastic waste streams and potentials for feedstocks from the deconstruction process. It is also possible for us to generate new polymers or even inorganic materials to broaden the potential value of plastics waste. Again, this approach requires coordination between waste markets and new product sectors. One of the themes here is a lot of systems integration. We can also reimagine the plastics production at the beginning of the life cycle. Can we innovate how we design products or synthesize new polymers towards a future where the entire plastics life cycle is considered at every stage of design and use? There is a need for more than one strategy to tackle plastics waste, but I will focus here on catalytic processes that can be redesigned to tackle new feedstock platforms. A key challenge is demonstrated here as we think about bond energies, going from, say, polyethylene to polyethylene terephthalate, is a wide range of bond energies across the landscape of the different types of polymers that we use because of the functionality of the polymers that are of interest to consumers, and even that are needed for safety and health reasons. For example, polyethylene has a uniform energy landscape where there's really no bond heterogeneity. So we have deconstruction products that are quite diverse. Polyethylene terephthalate, in contrast, is heterogeneous in the bond types, so that specific bonds can actually be targeted to selectively generate specific depolymerization products. That means that there's an immense interest in the catalysis community for us to really think about hand in hand across chemistry and chemical engineering to take advantage of this landscape. There's an increasing need for focus to design catalysts that promote high bond scission activity, but also have a means to control selectively products and therefore value that we can achieve from these plastic waste streams. Another component to solving the problem of redesigning processes is understanding that polymers do not behave as small molecules, which is where a lot of the knowledge around how we break down particular materials comes from. This influences things like chemical kinetics, absorption of molecules to catalyst surfaces, thermodynamic phase equilibria, and flow in large processes. Data science and machine learning can enable us to connect knowledge about processes from small molecules to larger macromolecule systems. Here's a case study from the Center for Plastics Innovation that illustrates this particular concept quite nicely. This is led by Dayan Lee and Ray Gordy at the University of Pennsylvania. They have a unique experimental approach that combines atomic layer deposition and capillary rise infiltration that has been developed to measure the effect of surface chemistry and polymer characteristics on the penetration and porous catalysts by macromolecules. Specifically, they're able to calculate contact angles and interfacial energies. By changing the identity and the amount of different oxides, we can achieve different contact angles. And therefore, we can study the impacts on conversion and kinetics for deconstruction. This is a powerful example of how we combine our understanding of catalysis and reaction engineering to obtain fundamental and accessible descriptors of plastics valorization that will allow us to target specific chemicals from plastic waste streams. There's been rapid adoption of old or more mature strategies from the catalysis field and applying them to converting plastics waste to value. And I'll highlight a few examples. Many that are shown here at the bottom are from the Center for Plastics Innovation, but there are many more. For example, on the left, hydrotreatment processes such as hydrocracking and hydrogenolysis, which has been taken from the oil and gas field, has been demonstrated to effectively lower the reaction time, temperature, and energy demand for polyolefin deconstruction. A detailed study of hydrocracking phenomena on LDPE shows that our understanding of classical hydrocracking mechanism translates differently to macromolecules, such that macromolecules react slower and can react more often. This phenomena leads to a direct relationship between catalyst metal acid site balance and product degree branching. Having more metal sites leads to more isomerized products, which may be valuable as waxes and modifiers in different markets than more less branched product systems. We can also use catalysts that have different mechanisms than simply deconstruction, such as using olefin metathesis chemistry. By using this approach, classical catalysts can be used to design systems that are agnostic to the waste streams or contaminants generated during activation and can produce monodispersed distributions of smaller molecule products that can be tuned for high value or specific target feedstocks. We can also consider reaction engineering pathways that move beyond individual catalysis methods to a network of strategies that enable selection of specific routes for select plastics waste or feedstock chemicals. And again, this is a partnership, which I'll talk about a little bit more later. Classical chemical engineering approaches take deconstruction products and convert them to molecules needed for a given process. This also aligns with many emergent strategies to functionalize waste, for example, to address waste complexity, where functionalization can enable separation or other targets so that you can have specific waste streams to generate specific high-value products. This logic model enables the integration of multiple approaches to minimize energy and maximize selectivity and value towards specific feedstocks. Beyond classical catalysis, nature provides us with a number of interesting strategies that can lower our consumption of precious materials, decrease energy demands, or increase process distribution. From the Blenner and Solomon labs at UD, one example is using mealworms to deconstruct plastics waste. This bio-inspired strategy enables lower energy consumption, but also importantly identifies biocatalysts that are useful for deconstruction of polymers on a large scale. This is also a potential pathway to expand the value of plastics waste by functionalization or conversion, which is an important strategy moving forward. There's more work that needs to be done to identify well-defined routes, but also in one recent example in the literature where we can combine things like homogeneous catalysis as well as biocatalysis as a way to do a one-pot method of adding value to plastics waste. Another strategy is also using bio-derived feedstocks as a platform to make new polymers. This concept is not new, but more attention needs to be given to designing these materials to be sustainable at end of life towards circularity, especially as we think about use in industry. One of the largest challenges in the future of valorizing plastics waste is the inherent diversity of plastics in general. We often look at differentiating types, plastic types shown in the top left here. However, this only looks at one attribute of plastics, which is, while important, is only one piece of the puzzle as we think about translating plastics waste into valuable feedstocks. Plastics are produced in many form factors, all the way from objects that we deal with every day to things like the pellets and powders that are shown here. And then on a micro scale to polymer films or powders and down to the micro and nanoplastics. These plastic products also have macro scale complexities to consider, such as multi-layer structures, co-materials like paper or aluminum, and mixed plastics waste streams. Inherent macromolecular features such as chain architecture, cross-linking, and the structure and processing histories of polymers also contribute to plastics waste complexity. Finally, the role of additives, often added to aid processing, impart functionality or durability or color, are also important for us to consider. These additives are particularly difficult to manage because of their large scale use. Think about the volume of additives that are used in plastic products and the molecular level contact with polymers in their product streams. So here's another case study, a recent paper in green chemistry from CPI that focuses on the role of antioxidants on HDPE catalytic deconstruction. Inherent additives in the base formulation of HDPE, simply obtained from a chemical supplier, so there's really no way to know exactly what's there, was shown to impact hydrocracking. From the top left plot, there's a significant decrease in conversion to liquids and gas that was attributed to the 4 small molecule additives present compared to what we would call pristine HDPE that's been completely stripped of any additives. If you take a closer look at the antioxidant chemistry, it highlights more nuanced changes in catalytic activity, where things like BHT leads to similar activity decrease and complex product distributions. A high performance additive severely poisons the catalyst, leading to low degrees of plastics conversion. And using IR spectroscopy, we were able to uncover how these different catalysts poison the system, either through active sites or consumption. And this is an important example of how we can benchmark catalytic conversion in the presence of real additives. I highlight here that there are key approaches to plastics waste valorization that include both scientific advances and stakeholder inclusion. Scientific pathways, of course, include our experimental research, computational modeling, data science, and systems analysis that are often at our disposal. But it also encompasses bringing together community partners, corporate leaders, public policy experts to tackle this challenge. And one of those challenges is that we must span multiple scales and multiple sectors in order to achieve this idea of taking plastics waste and converting them to valuable feedstocks. The smallest scale involves modeling molecules or macromolecules to design or define phenomena that are difficult to measure experimentally, using machine learning or artificial intelligence to increase the throughput of data collection. There are fundamental and applied experiments that are still needed to expand these scales to provide key data sets and parameters for us to do this. Systems analysis is also another approach that is critical to magnify the impact of the research opportunities, to connect the dots across the different catalytic methods to the inherent complexity of plastics to actually the value markets that we can use. And large-scale data sciences are needed for us to really have real-world adoption. This is a great example of how multiple researchers with different expertise and methodologies are needed to solve some of the same problems. I'll highlight here a few examples related to modeling at different scales using computational tools. Again, these are some examples from the Center for Plastics Innovation, where we have predictive tools that have been developed that vary scale phenomena across different reaction pathways and energy landscapes to model rate limiting steps in hydrogenolysis. We've also used computational strategies to predict macromolecular properties and then scale these results up with machine learning models trained on these new data sets. This is emerging as a potential strategy to model large-scale deconstruction processes, but also may be helpful for us to model the properties of these particular systems and how we can really think about targeting specific feedstock molecules. We can use this as a way to really design the future of sustainable materials from plastics waste. Data science is also valuable so that we can harness the power of research that has already been published. Using natural language processing, we can extract things like substrate identity, catalyst composition, and product streams from published papers, such that researchers across multiple centers, multiple industries can actually search for trends without performing new experiments or designs. Really, again, this idea of connecting what we already have across multiple approaches to target specific molecules. It's important that from a macroscopic viewpoint, key challenges are identified. For example, it's important for us to understand how well-defined tailorable product streams from any input plastics. We can use a chemical handle via transformation or a catalytic feature of a deconstruction process as a way to achieve specific materials that we need. Another challenge is having a robust strategy for dealing with waste complexity at multiple levels. The variation in polymer architecture, chemistry, additives, and impurities found in real plastics waste need large systems designed to separate valuable products from real waste and meet the challenges of global markets. This is a key place where academic research must take the next step toward addressing real plastics waste by considering both separation and reaction schemes. It's also important that we connect how certain pathways lead toward feedstock chemicals while enabling catalytic strategies. Integration across multiple scales and industries with LCA and TEA inputs is crucial, where we want to think about maximizing value, but in reducing environmental impact, energy consumption, the consideration of social equity, and cost. These challenges also require us to rethink plastics globally, not just at processes which utilize plastics waste, but also on minimizing plastics impacts to start with. We need to consider how we can modify plastics production by thinking about using renewable feedstocks, but we still need catalytic strategies to increase monomer selectivity from a sustainable feedstock perspective or conversion to polymers to new plastics. Industry really needs reliable and consistent renewable feedstock streams. We also can consider novel approaches to manufacture plastic products. Engineering polymers to have features that are unique and desirable requires catalytic and mechanical strategies to address complexity, but it is critical for us to consider problematic materials that may hinder valorization as we're designing new product streams. We also need to consider how we can change consumer use and perception such that everyday plastics may lose some unnecessary features, but enable sustainability and circularity. Another means of reimagining plastics waste with end of life in mind is by imparting inherent circularity to polymers. So inherently circular polymers are designed with purposeful breakpoints that can be broken on demand, typically under mild conditions and with catalysts back down to monomer. There have been considerable advances in this space, and many are shown here from the synthetic side, but it's important that we consider how these materials match conventional plastics in properties, manufacturability, and waste collection strategy. One example are these polyethylene-like polyesters, which show us that macromolecular structure can be generated using precise changes to the monomer chemical structure. And these monomer families can be designed or developed for a wide class of plastics with a single backbone, and therefore they can control degradation for these systems, but still have a range of functionalities. Biodegradation could lead to circularity if the degradation products are used to expand monomer feedstock supply. There are still remaining material challenges. The first is real plastics. As we discussed, they're heterogeneous at every level, and their potential harms and challenges for catalysis at every turn. And we must prioritize how we can be agnostic in ways that we use catalysis to enable specific material design. We can also think about multi-layer systems, which are challenging because they have many layers of different polymer chemistries with different additive profiles. Thermoset polymers are also a challenging class of material, and their network structure limits recyclability via conventional strategies. More work is needed in this space. And as I wrap up here, the key approaches toward innovation requires integration across all sectors. Everyone needs a seat at the table. There's no one size fits all. I'll just highlight here the communication around public policy as well as educational opportunities so that we can really think about both consumer education as well as training the next generation of science and engineering students. There are many cross-collaborative opportunities where specific deconstruction products must consider the complication of all of the things that I've talked about today. And then we really need to think about combining polymer engineering, catalysis engineering, and process analysis and engineering, and to really consider end-of-life management across all of these sectors. And then I'll just end that we still have a mountain of waste to climb as we consider materials development. New chemistries are needed, new catalytic processes, but really this systems level thinking is appropriate as we start to target taking plastics waste and creating new specific targets for new polymer development. And with that, I thank you for your attention and welcome any questions.
Thank Thank you, LaShonda, for that excellent presentation. We'll now open the floor up for questions, both in person and also just a reminder, please do the raise hand function online. And we really encourage you to be part of the dialogue for those who are joining us virtually. So any questions? Looks like we'll have one from in person first. Susanna.
Thanks, Susanna.
Good to see you again. So I have maybe a provocative question. Sorry, did you hear what I was saying, or shall I repeat?
I can hear you now.
You can hear me now, okay.
Okay.
So Susanna Scott from UC Santa Barbara. That was really comprehensive. And I have a provocative question for you.
Sure.
Okay. So your presentation said there's room for everybody. We should consider every single possible approach to this problem. And you also said we need a systems level approach. So I wonder how you think about a systems level approach, which is completely uncoordinated, which seems like where the research community is right now.
Right.
And if we really want to have an impact on this problem, what could be the role of taking a more coordinated or strategic systems level approach to it?
Right. So thanks for that question. To me, that is the challenge, right? So there are many people who are working on different classes of materials. They're taking, more classical approaches. Some people are doing biocatalysis, and the communities typically don't interact until we see a publication, right? And so when there's opportunities. So and I think there's a part for those who are leading in this space to get together and start to have conversations about how we can integrate some of these technologies. The larger problem to me, we can think about, designing and optimizing and having a systems level approach here, maybe in one geographical region, but every place is different. And so, the global nature of what we're doing to me sometimes makes it feel intractable. But I think we still need to have a conversation about how we can use these different approaches, because even the having a suite of different types of approaches allows one to consider even from a geographical perspective. If we have all of these different approaches, we know that, approach X enables this particular feed stream, it has this particular tolerance. Maybe that implementation at a specific, geographical location that only has a specific type of sorting, or they only collect, this particular type of material may be enabled. But we need to know where they are. We need to know those boundaries. And then I think there are other people who need to sit at the table to help kind of direct this process flow for us. I hope that helps spark the discussion a little bit more.
That's a very good answer. Thank you.
Anybody online? Again, we're happy to take questions. Please just remember to raise your hand first. At this point, we'll take a question in-house. So Jack.
Very minor point. You mentioned a recent review, and I didn't catch the place or the author.
Oh, sure. So it is an annual reviews of material research, and I'm the corresponding author for that, myself and Thomas Ups. Yep.
Okay.
Yep, 2022. Yep.
Great, thank you. Crickets online, anybody? We'd appreciate the input. Okay, back to Jake.
So the producers still do put those little numbers in the triangle. And do you see any space for just ordinary consumers trying to separate those plastics again through some sort of sorted collection mechanism? Or do you think that, it didn't work in the past, it's just not going to work in the future?
My understanding, and having talked to some of the waste treatment facilities here in Delaware, is that I think that we've reached a point where I think consumers are comfortable with our current collection strategies, right? I think that we have to figure out from a sorting facility perspective how to deal with some of these challenges. I don't think that we I think we want to educate consumers about kind of use. I think more so from a consumer perspective, helping, if you think about, if we say we take a sustainable feedstock and we make a new material system out of it, right? So we'll have a new class, a new number, right? Thinking about the differences that may come from that, right? So maybe it's how it feels as you touch it, or there's some visual differences. It still performs the same way, but helping consumers, helping all of us adopt to change as we start to use, more recycled materials, as we start to use more bio-based feedstocks. I think that is something that we can help and start to educate as a community.
Thank you. LaShonda, I actually have a quick question.
Sure.
So along the lines of additives, sort of the report you showed there was more as a poisoning aspect, and that's certainly true. But do you also see that as a potential opportunity if those are designed in a way to, so you could just comment on that briefly?
Oh, absolutely. So yes, I think that, we don't always have to view additives as inherently dangerous to deconstruction, right? So I think we need to understand how additives are imparting specific challenges to different processes, and then work hand in hand with industry to think about ways specific additive profiles may be changed or how they may be used beneficially as we start to think about new pathways for deconstruction. So we're starting, to really try to have those conversations as well.
Great, thank you. Last call, in person or online? Okay, let's thank LaShonda again for a great talk. So it's now my distinct pleasure to introduce Professor William Tarpey. Dr. Tarpey is an assistant professor of chemical engineering at Stanford University, and he's also a member of the SunCat Center for Interface Science and Catalysis at SLAC National Lab Accelerator. His lab develops and evaluates selective separations in wastewater at several synergistic scales. He's going to tell you much more about that. But he also investigates molecular mechanisms in these systems while also interrogating systems level assessments that identify optimization opportunities in the space. Some of his prominent distinctions include being named to both the CNE News Talented 12 and Forbes 30 Under 30 in 2019. Recently, he's a recipient this year of both a Camille Dreyfus Teacher Scholar Award as well as a 3M Non-Tenured Faculty Award. Let's all welcome Professor Tarpey, who's going to tell us about electrochemical wastewater refining.
Good morning, everyone. It's a great pleasure to be with you here today. I decided to take on the task of continuing on what LaShonda talked about with unconventional feedstocks and talking about wastewater. So this is your morning primer on wastewater and about wastewater refining and the roles that catalysis and catalytic separations have to play. I decided to start with this photo because it shows formerly the Blue Plains wastewater treatment plant for those local to DC, and the Woodrow Wilson Bridge is in the background, and I grew up just on that side of the Woodrow Wilson Bridge. So Blue Plains, as it was formerly called, used to be something you could smell from the bridge. And now it's really one of the leading wastewater facilities in the country, if not the world. And so that's been a great thing for me to see over the course of the past couple of decades or so. And I want to dig into a little bit of how Blue Plains and other wastewater treatment plants have managed to really start a revolution when it comes to wastewater refining. So let me make sure I have the slides going. Perfect. So I like to start to think about wastewater and why to treat it from a framework called planetary boundaries, which was popularized by Rockstrom et al. And so this is starting with some systems level thinking right off the bat. So the way to think about this graphic is that each of the dotted lines of the circles you see is sort of a range of carrying capacities of what the planet can handle across these different categories. So climate change is one of the ones we're most familiar with, of course. And so I focus most of my work on biogeochemical flows. The colors and the sizes of these pieces of the pie denote how far beyond the carrying capacity we are, how at risk we are in that category. And so you can see that for biogeochemical flows, we're far out of scope in terms of what the planet can handle. One quote I find quite motivating from our Buckminster Fuller has to do with how we think about pollution. And in short, in my group, we think about pollution as simply misplaced resources. The very same molecules that we call pollutants in wastewater, if they're somewhere else and in high purity, we simply call commodity chemicals. And so much of our work is about how do we catalyze reactions and also achieve highly selective separations to convert, so to speak, these pollutants into products. So most of the time when we think about wastewater, we think about it as something that costs us things, whether it's money, energy, or chemical inputs. So if we look at the national EPA budget, this is from a few years ago, we spend around $270 billion on treating and transporting wastewater. A plurality of this in red and orange comes from secondary and advanced wastewater treatment. And so to step you through what that means, primary wastewater treatment is broadly speaking removing solids from wastewater. Secondary treatment is removing dissolved organic carbon from wastewater. And advanced wastewater treatment is frankly everything else. So whether that's removing nitrogen or removing phosphorus or removing trace organic pharmaceuticals. So in California, where I spend most of my time, we spend around 20% of our state energy budget on treating and transporting water and wastewater. So wastewater treatment costs us energy. Finally, it costs us chemical inputs. You can see the biggest share here, again, flocculation and coagulation. That's the primary treatment, the first step of wastewater treatment. And then we see even disinfectants in the third, the tertiary or advanced wastewater treatment can cost us chemical inputs as well. So for today, I'll focus mainly on nitrogen because nitrogen, there are several nitrogen small molecules that are of interest to my group. And so we can think about the case for wastewater refining really has to do with how to re-achieve circularity, so to speak. So the nitrogen economy has always been circular from a natural nitrogen cycle perspective in terms of cycling between inert nitrogen and reactive nitrogen, all the other forms besides dinitrogen. And so you can see this is well balanced between biological nitrogen fixation largely, and then storage and denitrification that largely occur in soils. Humans, we've skewed this cycle towards reactive nitrogen, and we've also doubled the throughput of a reactive nitrogen in the environment. And so for reference, for carbon, estimates range between us changing that about 10 to 50%, right? For the carbon cycle, nitrogen cycle, you see we've doubled it. So that's 100% change, right? And so this is just me saying we should include nitrogen in this conversation as well. This nutrient removal you see here is for wastewater treatment plants, and you can see it's far outpaced by Haber-Bosch fertilizer production. And so what we do as a group is try to recycle this reactive nitrogen in place, and like I mentioned, resituate it so that it's not a pollutant anymore, but it's a valuable product. And so one of the ways to think about this, and I'll show this in more detail later, is being able to catalytically convert waste products, so to speak, like ammonia and nitrate into other intermediates and to these end products as well, but in a highly pure state. And so we do this using electrocatalysis mainly. So some of the consequences of this nitrogen management, this acircular nitrogen management or linear nitrogen economy, are that we of course see environmental pollution. This is a picture of an algal bloom that's facilitated by megatons of nitrogen being emitted into surface waters. And so the number of these algal blooms, these dead zones that are a result of over-consuming oxygen due to over-fertilization of algae, more or less, has exponentially grown over the past 7 decades. And so this is a problem that we don't really have a solution for. And this in particular is outside of Cleveland and Lake Erie. With Haber-Bosch, we also emit carbon dioxide, and as has been talked about in this meeting, much of that is due to steam methane reforming from the hydrogen that goes into ammonia production. As LaShonda touched on in terms of equity for plastics, this is also an equity issue when it comes to nitrogen management. That's because there are fewer than 100 Haber-Bosch facilities around the world. And so that means that people who aren't near any of these black dots pay an upcharge basically in transport of fertilizers, and we all pay an upcharge in terms of the emissions that go towards transporting these nitrogen fertilizers. You can see a big paucity of these in South America, and in sub-Saharan Africa is shown here. And so someone in Mali who on average makes 30 times less than someone in the US actually pays twice as much for their fertilizer per gram of nitrogen. So we think about wastewater and how this can potentially address some of the challenges we're facing when it comes to circularity for nitrogen. And so we can compare the nitrogen that's in wastewater in green in terms of megatons of nitrogen per year over time to the Haber-Bosch nitrogen production. And around 30% of total Haber-Bosch could be offset by the nitrogen that's in municipal wastewater and in fertilizer runoff. Not 100%, but 30% of one of the largest chemical manufacturing processes is something worth, for me, committing a career to, so to speak. Now, in terms of which of these reactive nitrogen species we should go after, often a conversation happens, should we focus on ammonia, total ammonia nitrogen, or should we focus on nitrate? And the answer is sort of all hands on deck, both, because when you think about both the concentrations as shown here and the volume or the volumetric production rate of these wastewaters, you end up around the same order of magnitude. There are relatively equal opportunities between recovering ammonia, recovering nitrogen from ammonia, and recovering nitrogen from nitrate. And both of these are pollutants in various wastewaters. So the project we're considering at this point is what we're calling wastewater refining. We use refining on purpose because as chemical engineers, we're sort of borrowing from the concept of oil and gas refining, right? Where a crude feedstock comes in, you develop many unit processes and tune them to make dozens of different products. We're thinking about the same thing, but for wastewater. So to characterize that opportunity, how we've done that so far is looked at global flow rate of different wastewaters on the x-axis, total dissolved solids on the y-axis, and then each of these pies you see is a different wastewater, broadly speaking. The size of the pie is proportional to the amount, the value in terms of billions of dollars that's in that wastewater globally. And then the pieces of the pie are the mass compositions, the mass concentrations of different components, right? And so you could say, if I want to recover something like nitrogen in green, I would focus on municipal wastewater shown in the bottom right, or I could focus on hydrolyzed urine shown kind of in the middle toward the top. And so this is what we're trying to do to help people establish opportunities and say, hey, if you want to recover phosphorus, go after pulp and paper wastewater, right? A little bit of a framework here, which ties into Susanna's question for LaShonda about coordination, right? How do we coordinate a strategy that allows us to valorize wastewaters at a very urgently needed scale and rate? And so what this comes down to is that this is going to take catalysis, of course, but it's also going to take separations. And so you can think about capturing a pollutant as removal, purifying a product as recovery, and then anything that combines a reaction and a separation as refining. And so why do we use electrocatalysis in particular? Why do we think this is a good fit for wastewater refining? First of all, electrocatalysis is quite modular, flexible scale. So we can do this at the toilet scale or the building scale, all the way up to a citywide scale. Secondly, we can integrate it with renewable energy. And so this means we can, frankly, just hook it up to a solar panel. So one of my students did this last week, and I was screaming in excitement that we were able to do this for the first time, but actually just hook up some of our electrocatalytic water treatment to solar panels. We can also replace chemical inputs with electricity. And so this means that we can produce acid and base on site, for example, and tie in wastewater refining to many other chemical commodity manufacturing processes. And lastly, since electrons are a major reagent, we can control the delivery of these either through current or control the applied potential. And so these can take shape in many different engineered reactor setups or formulations, from electrodialysis to capacitive or ion insertion, which borrows from the battery literature, all the way to a more typical electrocatalysis, excuse me. So within catalysis, we, especially being wastewater engineers, like to really focus on both sides of the electrocatalyst and electrolyte interface, which may not sound particularly revolutionary, but we have found that broadly speaking, the electrolyte tends to be undercharacterized when it comes to catalytic research. And as wastewater engineers, we don't have the luxury of just like choosing our electrolyte often. It's uncontrolled composition and it's quite variable. So we really study this in careful detail. I'll show you some strategies we use to actually control the electrolyte. I'm being a bit glib there, but in short, we approach this thinking a lot about the electrolyte. So I'm going to focus on the reaction of nitrate reduction to ammonium, which you can see as a multi-electron, multi-proton transfer. So quite complex, lots to study here. But I want to first give a picture of how we approach this. And so first, most of the time, and of course this is very needed research, we, broadly speaking, the field focus on electric catalyst structure, chemical composition, crystal structure. And then we and others are also thinking about electrolyte properties. What's the pH of the solution? What are the species concentrations? And for electrocatalyst structure, we're used to in the field thinking about initial structure and then surface reconstruction over time or over the course of the reaction, right? An analogy in the electrolyte is thinking about the bulk composition far away from the interface versus the interfacial composition and mass transport being the mediator there, right? So we might observe, or we have observed, a very high alkaline pH near the interface during nitrate reduction, even when we use a very acidic bulk composition of electrolyte here. And so language that's being used here a lot is the reaction microenvironment. You can also just think about it as both sides of the electrochemical interface here. And all of these factors affect our observed activity and selectivity. So it's a fun puzzle to really tease apart here. And so what these refineries look like, bringing back to this oxidation state ladder, is that ideally our vision is that we should be able to make any inorganic nitrogen species on this ladder, especially because some of them have very unique uses, right? Hydrazine is a common fuel. Hydroxylamine is a precursor to many pharmaceuticals and CN bond formation. But we should be able to make any of these through a reductive and an oxidative pathway, depending on the situation. So be able to tailor reactions to realize this refinery vision. So I wanted to give just a sample of some of the techniques we use here. So electrochemical stripping is one of our most mature approaches, and it's a variation of electrodialysis that allows us to recover highly pure ammonia solution from really multiple wastewaters. And so electrodialysis is happening between a titanium mixed metal oxide anode and a stainless steel cathode in most cases. We have a wastewater that has ammonium in it going through the influent chamber. And then we have a dilute salt solution just to ensure conductivity, and then an acidic trap solution. And we chose to make ammonium sulfate here because it's a relatively common liquid fertilizer. In this anode chamber, we achieve acidification via the oxygen evolution reaction. And so ammonium is the predominant species of total ammonia nitrogen. Ammonium and other cations will cross through the cation exchange membrane via electrodialysis to applied electrochemical potential. And at this cathode, we'll achieve hydrogen evolution. And so we will increase the pH here. As this happens, we will deprotonate ammonium, make ammonia, which is aqueous, but will start to volatilize, especially as the pH increases well above 12. Now this ammonia is volatile, and we can select for it with a porous gas permeable membrane, often made of polypropylene, that allows us to recapture and reprotonate this ammonium in a more stable form. So we've selected for ammonium nitrogen based on first charge and based second on volatility. In short, ammonium is the only compound that really passes both of those tests, so to speak. So these are data from real urine being fed into electrochemical stripping. And you can see from this nitrogen mass balance that we can recover the majority of the ammonia that was in the anode in green. It goes through the cathode in black and ends up in the trap. And so we've managed to do this, like I mentioned earlier, for several different wastewater. So really any wastewater that has ammonium in it, we can selectively recover ammonium from it on the order of 90% recovery efficiency and with very high selectivity. So from this, we've moved on to other reactor setups that allow us to really integrate nitrate reduction here as well. And so this electrodialysis and nitrate reduction reactor that we've engineered uses dynamic bias, which is what we call the phenomenon where you switch where you apply the potential and the magnitude of that potential, such that you can achieve different types of recovery based on the stage you're in. So the first stage, we do basically electrodialysis through ammonia recovery. And the second stage is where we're actually synthesizing ammonia from nitrate. So if you want, you could think about this as ammonia made in two ways. And so in the electrodialysis stage, we're feeding in ammonia into this middle chamber and then separating ammonium in the right and nitrate in the left. And you can see the circuit is connected between the two outer chambers. Now we switch where the circuit is applied. It's between the left and middle chambers. And importantly, the left chamber that was an anode is now a cathode. And at that cathode, we can facilitate nitrate reduction. And so this is what I meant by, I was being a bit glib about saying we don't have control over the electrolyte. What we've achieved here is that we're doing nitrate reduction in an electrolyte of our choosing. The wastewater is still in the middle chamber, but we're achieving nitrate reduction in a controlled electrolyte. And we can really control what's happening in this electrolyte. So moving forward here, what we've done is really, in the name of looking at both sides of this interface, we've looked at both the electrode and the electrolyte. From the electrode side, through our collaborations within SunCat, we've managed to investigate the nitrate reduction surface structure after reaction through a combination of grazing incidence, X-ray diffraction, and X-ray absorption spectroscopy at the synchrotron, and also through collaborations with computational colleagues using density functional theory. And so we were able to control this titanium hydride formation and identify titanium hydride as the major component of this surface. And then further, this is just showing some of the GIXRD data where you can see the experimental stage in the middle starts to look more like the titanium hydride reference at the top than it does like the titanium foil at the bottom. Now, in terms of the electrolyte, we've shown through several pairs of different electrolytes that you can see improved performance in terms of higher bars when we use sodium over potassium. And so this has to do with waters of hydration, and we're investigating mechanisms here now, but these are observational for now. And then we can also see higher performance when we use perchlorate over chloride by comparing the middle two sets of bars. And finally, increasing the concentration allows us to achieve higher performance as well. We can also do this for pH and see that the lower the pH, there's kind of a regime shift around pH 2. If you're just below pH 2, you get much higher performance than you get above pH 2, which just has to do with the nitrate to proton ratio. So putting all of this into practice, what this means is we can engineer this nitrate reduction microenvironment quite intentionally. We can design the electrolyte by just controlling how long we do electrodialysis for, so that the pH gets quite low. Just by how long we run the first stage, we can purposely form titanium hydride, and then we can use real reverse osmosis concentrate with a composition shown here and observe a over 3 times increase in performance as we went from simulated to real. So a much more complex solution, but with these kind of tricks from the engineered nitrate reduction microenvironment, we're able to observe improved nitrate reduction efficiency, which is shown on the y-axis there. So as I wrap up, I want to just show one other example, especially because we've been talking a lot about life cycle analysis. I wanted to show some results and insights from life cycle analysis and what that can do for us. So another part of the work that we really focus on is trying to integrate electrochemistry with selective materials. So think it's sorbents or membranes that are truly ion selective. So one of the first things we found was when we were trying to do this from concentrated nitrogen waste streams, we did a life cycle assessment of a technology that was not developed yet. So I want to emphasize that life cycle assessments can be prospective. They don't just have to be retrospective. I think often we say we need to wait until we can do a life cycle assessment, but we can do them often sooner than we think, and they can actually drive innovation at the lab, back at the lab scale. So here what we found is we split up this recovery setup, so to speak, among the different life stages of nitrogen recovery from urine in this case. And the biggest piece of the bars you can see here is actually acid manufacturing, is the regenerant, right? And so that's not something you would necessarily guess beforehand unless you study ion exchange a lot and you know that the Achilles heel of ion exchange and adsorption is often the regenerant solution you need because it's concentrated acid, base, or brine. And so with this insight, that drove us to think about different ways to regenerate an existing ion exchange resin, in addition to developing novel ion exchange resins. So naturally, we used electrochemistry to do this and generated pH 11 and 3 solutions in an XC2 way and then fed them in. And then to further reduce the environmental impacts of this, we actually used electrons simply to regenerate the ion exchange resin. So by combining these selective materials with selective electrochemical processes, we already know that this is going to impact the biggest piece of the pie, which is the regeneration. So as I wrap up here, I want to just show sort of like a zoomed out picture of how we think about this in terms of integrating these wastewaters with different types of electrochemical tools can really help us to guide not just use-inspired research, which is quite excellent, but also use-informed research. So how do we design electrocatalytic processes and materials that are designed from the start for the challenges of real wastewater where things need to be quite robust and have a long lifetime, yet have molecular level control. So from this, our formula really is thinking about available wastewaters, what value propositions, what do you want to make, and then what tools you can use. So I've shown some electrocatalysis today, a little bit of electrochemical separations, and then we can also think about stoichiometric electrochemical conversions like precipitation, or also mediated bond formation. And then to go through this, we can take the target pollutant, think about solute influences and our target products, and then those value propositions. So with that, I will wrap up. I've talked about nitrogen in detail, but want to make sure we're thinking about other elements as well. So phosphorus is another, lithium from spent batteries, and then we can also valorize desalination brine as well. So hopefully I've given you a little tour of wastewater refining. I definitely want to acknowledge my group and some of our funding sources. Those in bold are some of the work I showed today. And with that, I would love to take your questions. Thanks very much.
Thanks a lot, Will, for the great talk. We'll now open up both in person and virtually for questions. Just remember online, please raise your hand so you'll come to the top of the screen and we can identify you. Oh, in person, please.
In person, great, thanks. That was a wonderful talk, very interesting and inspiring. Thank you.
Thanks, Ryan.
Appreciate it. I was wondering if you could comment a little about the economics of on-demand acid and base generation, more generally, and does it offset shipping costs, and how does it relate to the chlor-alkali industry? And is this sort of happening, or is it more of a lab curiosity? By happening, I mean, is it being commercially implemented and stuff like that? Thank you.
Yeah, great question, Aaron. Broadly speaking, I would say as we start to have some of these life cycle insights where both companies and wastewater treatment plants are realizing how much money they spend on acid and base and transporting it, especially some of those that are more remote, I think it is starting to happen. So there are facilities in California where they're actually generating acid and base from desalination brine, for example, quite salty, great for electrochemistry. And that's coming out of some of the insights that 60 to 70% of the costs at a wastewater treatment plant, depends on the plant, of course, can go towards chemical inputs. And so with that insight, then facility directors are like, okay, how do we cut down that cost? So I think it's somewhere between happening at scale and a lab curiosity, but it's really scenario specific, where again is where the typology of scenarios really helps, because when we talk to wastewater treatment plants, it helps to say like, oh, a treatment plant that has a similar flow rate to yours is doing this, right? That's how we can kind of start to scale the innovation. Great question.
Sarah?
Hi, Sarah.
I will. Great talk. I had a question about the heterogeneity of your wastewater, like urine versus from a plant. Does the different nitrates and nitrogen species change how you do this? Like, would you change the pH? Would you change? And then are you targeting nitrate specifically, or do you think you're also getting nitrite and hydrazine and all the other things being reduced at the same time?
Yeah, really being reduced or produced?
I'm sorry, being reduced.
Oh, being reduced, like they're present is, okay, yeah, got it. Just want to make sure I heard you, because that's an important consequence of how I answer. So yeah, so we tend to think about, like going back to that graph I showed of all the different pie charts, some of the nitrogen is present as ammonia, and or let me put it this way. In some wastewaters, nitrogen is predominantly present as ammonia, and in some it's predominantly present as nitrate. So we've developed a lot of ammonia selective separation techniques, and we're starting to design some ammonia selective oxidation as well, oxidation techniques. But much of the wastewater that's not controlled, like non-point sources, has a lot of nitrate in it. Nitrite is not so common as a pollutant unless microbes have slightly reduced nitrate to nitrite. So in short, but for the EDNR process, we said, oh, what if we could take a wastewater that has both ammonia and nitrate, or mix two wastewaters, one that's ammonia rich and one that's nitrate rich. So in short, ammonia and nitrate are the most commonly occurring wastewater pollutants. The other species we tend to make, or microbes have made, but would be present as far minority species. Yeah, I see there's a hand raised from Marty Burke. I think you can go ahead.
Hey, thanks so much. Hi, Will. Marty from Illinois. Really awesome talk. And I'm just wondering, as the consequences of climate change kind of manifest themselves over the next 10, 20, 50 years, how do you imagine wastewater management kind of evolving in the context of that scenario?
Yeah, that's a great question. I think in 10 or 20 years, especially as water scarcity increases, and of course that happens more in California than it happens here, for example. But I think as people realize that wasting water doesn't really make sense as a concept when water is scarce, I think that's sort of a trampoline for us to think about what else are we wasting in the wastewater that we could recover as well. Another small thing that happens as water becomes more scarce is that wastewater becomes more concentrated. So as people use less water, then the wastewater becomes more concentrated, which makes our job sometimes easier, sometimes harder, but it's just a change that we need to be aware of. So everything is more concentrated besides the water.
Great, thanks.
Sure.
In-house?
Yes, thank you. Great talk. So wastewater isn't, as you've sort of pointed out, isn't one thing. It might have different concentrations of all sorts of different things. But what point of the process do you see your technology being deployed? And is that something that like has to be retrofit in, or is it like, oh, okay, we've just removed the solids and now it's time to produce ammonia? How does it mesh with what's currently there?
That's a fantastic question. So in terms of where among primary, secondary, and advanced treatment, everything I've shown you is within the advanced treatment section. So solids have been removed already. Dissolved organic carbon has likely been removed. Now, some of these more niche wastewaters, that might not be the case. Like for urine, if it's separately collected, we would just treat it straight. We might need a little bit of pretreatment, but we would effectively be doing like a small version of solids removal. And then we would go through our treatment processes.
Thank you so much.
Sure. No questions online, but feel free to raise your hand.
Hi, very nice talk. So I had a question about the nitrate reduction. So given that you want nitrate in fertilizers and in a way making nitrate by Haber-Bosch followed by oxidation of the completely reduced nitrogen is inefficient,
but necessary. I was wondering if there could be more direct route if you go to the wastewater where the nitrate is present, if you were just able to separate it effectively. And do you have any leads on how to get it out as nitrate?
Yeah, so just a separation, not a reaction there. Yes, so we can use ion exchange resins, and we're also trying to design selective ion exchange membranes for nitrate. And so broadly speaking, I think your question, Karsten, also touches on like, there's so many different separation plus or minus reaction routes for this nitrogen cycle, right? And so what the refinery vision allows us to do, at least for now, is to say, we need to establish so many of these that all is fair game, right? And so yes, some of them in different, and with the kind of caveat that in different scenarios, some will be more useful, but we need to like move the TRL up on all of this, right? And so that allows us to say, sometimes nitrate, we might just want to do a nitrate separation. Sometimes we might want to oxidize ammonia to nitrate, then do a separation, right? Sometimes we might want to do the exact opposite of what I just said, right? But yeah, so nitrate removal is a little bit mature in wastewater, but mainly for drinking water because it's a drinking water pollutant. And so people have removed it, but not really thought about recovering it from the ion exchange resin.
Question in person.
Nikki Bull, Indiana University. Super important work, especially for those of us who live in the Midwest and have to deal with the most polluted water in the world. How do you envision this working at the farm level? Because most of the nitrogen excess is Haber-Bosch. Do you envision lots of little plants that farmers have at their waste runoff, water runoff, and then they produce ammonia that they store for the next season? Or how do you envision this, and what do you envision the cost being versus buying the ammonia originally?
That's a great question. All of those questions are things we're still honestly working on. We don't know yet, but through we're working on an distributed ammonia manufacturing project where we're collaborating with 2 chemical engineers, an environmental engineer, and 2 agricultural scientists who are really helping us think about what happens at a farm. So tile drains have been a thought, right? Like you were getting at. But it also ties into a really big question. I just showed like sensors for like a second, but it also ties into, can we miniaturize some of these electrochemical processes to be sensors so we know, get a better sense of where the most concentrated non-point sources are, if you will. And if that could be achieved, could those sensors also have actuators that allow them to actually recover the ammonia, right? And so that's kind of an out there idea that's about bringing the treatment to the water rather than bringing the water all the way to the treatment, so to speak. Yeah, which is a huge challenge, but your point is very well taken. As a wastewater person, we talk a lot about nitrogen removal and recovery, but like 80%, 70 to 80% of these of the pollution is non-point sources that aren't from a pipe that we could put a device in. Yeah, really great point. Still no hands raised online, so I guess we'll go to an in-house one.
Hey, so I think out of the University of Delaware, they've started to do some work to couple, say, CO2 reduction and nitrogen chemistries. So I'm wondering if what you think the I guess space for generating kind of commodity chemicals from nitrogen other than fertilizers might be in the future.
Yeah, really great question. For me, I think from the wastewater side, we broadly speaking have been focused on fertilizers for several decades, which I think are exciting, but have incredibly low profit margins. And so that means that I have to be really cost effective at doing my job, right? Producing higher value chemicals gives me a little more wiggle room, right? And so I think that's Feng Zhao's work that maybe you were referencing, which is excellent. And my colleague Tom Jaramillo is doing some work on that too, just because he's done a lot on CO2 reduction. For me, it's like the higher value we can make, the better, right? And so I was really, for me, that like the thought I was having was, I think from Todd's talk, you were talking yesterday about how to pair biocatalyst with electrocatalyst, or I read it as electrocatalyst. That's not what you said. But thinking about how we can do cascades to increase the value of what we produce, basically. Yeah.
Thank you.
Sure. There's one question online if there's time.
Yes, please go ahead and unmute.
Jenny, go ahead and unmute. Hi, Jenny.
That was really great, William. I really loved hearing your talk. My question was, since you mentioned that you work with soil scientists and have been thinking about how this works on a farm, you know, one thing that I often think about is that N2O is the third most significant greenhouse gas. And based on what you're trying to do, could that also reduce sort of that, you know, runaway production from agriculture?
Yeah, absolutely, it can. So another source of N2O is actually wastewater treatment plants themselves. So one of the hardest things to do, I feel like for the past 15 years, people have been trying to really track how much N2O is emitted from wastewater treatment plants through incomplete oxidation, largely during wastewater treatment, and similarly for soils. And so some of this diversion of nitrogen from municipal wastewater treatment plants or through different processes can help us reduce the amount of N2O that is emitted from wastewater treatment plants. From the soil, I think that has to do with how stable some of these fertilizers can be, such that they don't end up volatilizing as N2O.
Due to the interest of time now, let's thank Will for this great talk and great discussion.
Welcome back, everybody. My name is Carlos Gonzalez. I'm the chief of the Chemical Sciences Division of the National Institute of Standards and Technology, NIST. And I'm going to be chairing this session, which is the last session of our workshop, Vistas in Catalysis. So for this session, the planning committee actually solicited abstracts from researchers of different career levels in order to give an opportunity to actually tell us a little bit more about their research, focused in different areas such as, let's see, let me look at my script here, catalyst discovery, novel applications of catalysis, and also development and use of new techniques to help understanding the mechanisms governing some of these catalytic processes. And from the many abstracts that we actually received, the committee has actually selected 14 abstracts for very short presentations, 3 minutes each, and what people call elevator talks, where I work. And so because of that, in the interest of time, we're not going to be able to actually ask questions after the presentations. If you have any comments or suggestions, epiphanies, please save it for the end. At the end, we're going to have some time to actually reflect on the presentations. And also, in order to, in the spirit of inclusivity and flexibility, the committee gave the presenters the choice to actually present in person or actually send recorded videos of their talks. And so far we had 11 presentations that are going to be presented via video recordings, and the last 4 are going to be in person, right? So all the abstracts and the contact information from the presenters is available online for you to look at. And if you have any questions, I'm pretty sure that the academies can actually help you to find that information, right? So again, as I said, the time, so please keep your comments to the end. We're going to have some time to do that. So let's actually move on, and we're going to present the first 11 presentations, which is going to be recording videos. Why don't we just move to the first one? The first one is from MD Estak Ahmed. And by the way, from the very beginning, I apologize to the speakers if I mangled your names, and I'm sorry about that. So he's from Michigan State University, and the title of the presentation is Electrocatalytic Ammonia Oxidation by Low Coordinate Copper Complex.
Good morning, everybody. Today, I'll be talking about electrocatalytic ammonia oxidation using molecular copper catalyst. Due to the depletion of fossil fuels and increase in global warming, we need some alternative carbon-free sustainable source of energy. Ammonia is an especially appealing and attractive source of energy due to several reasons, like high energy density, easy transportation, hydrogen storage medium. It can also be used in a direct ammonia fuel cell. Ammonia has strong NH bond, even stronger than methane. So to break the NH bond, we need a catalyst. Our goal is to develop some molecular catalyst based on fast flow transition metal elements, which can oxidize ammonia electrocatalytically at low over potential with high rates. This is the beta diketaminate copper catalyst. When I add excess ammonia, it forms copper 1 ammonia complex. This is the CV of copper 1 acetonityl bound complex, which shows a nice reversible redox process. When I add ammonia to this electrolytic solution, we see a large catalytic current. The catalytic current increases with increasing ammonia concentration and catalyst concentrations. And the overall rate is first order with catalyst concentration as well as ammonia concentration. T of max is determined from standard dependence to be 940 per hour. To determine some kinetic parameters, we performed ammonia oxidation in ND3 instead of NH3, and from the slope, KHKD value is determined to be 2.4. This indicates deprotonation is involved in rate determining step. To analyze the products, we perform CPE experiment, and headspace gas analysis shows formation of hydrogen and nitrogen. Long-term CPE experiment shows the catalyst is pretty stable. Based on electrochemical and chemical data, we have proposed the catalytic cycle of ammonia oxidation. First, the copper-1 ammonia complex oxidized to form copper-2 ammonia species. Deprotonation in presence of excess ammonia forms highly reactive copper-2 amide intermediates, which readily dimerizes to form copper-1 hydrogen. Bound hydrogen is then displaced by excess ammonia and oxidized under electrocatalytic conditions to nitrogen. All the intermediates are isolated chemically or spectroscopically. At low potential region, we observed a reversible redox process which depends on ammonia concentrations, and this is due to the formation of bis-amine complex which is catalytically inactive. In conclusion, we can say that polyamine copper-2 species are stable for years, but the 3-coordinate beta-diketaminate copper-2 complex is unstable with excess ammonia. The deprotonation of copper-2 ammonia complex is the key factor for ammonia oxidation. By changing the substituents, we can tune the overpotential and rates of ammonia oxidation. In future, we'll focus on bulky ligand design to prevent the bis-amine formation.
Let's move to the next one. The next one is actually presented by Anastasia Alexandrova from the University of California, Los Angeles. And the title is Dynamic Catalytic Interfaces, Ensembles of Metastable States, Break the Rules of Catalysis.
I will be talking about dynamic catalytic interfaces, particularly those that do not stop undergoing their dynamics in reaction conditions. Typical and convenient assumptions in theoretical catalysis are such that the active site always stays the same. We therefore have convenient BEP relationships as well as linear scaling relations, which are very convenient for catalyst design from the point of view of adsorption strengths of key adsorbate intermediates in the reaction that have to be neither too strong nor too weak. However, there is a lot of experimental evidence that both thermal and electrocatalysts undergo strong morphological changes and often dynamics that doesn't stop, that strongly depends on reaction conditions such as partial pressures of gases, temperature, applied potential, and adsorbates. As modelers, we have to approach these interfaces differently. Specifically, we should stop focusing on just the global minimum of the most stable form of the catalyst in reaction conditions, but instead encompass all accessible local minima, which could differ in geometry, stoichiometry, and site on a support for supported catalyst. This dynamic ensemble changes together with the catalyst reaction. We have to view it through Boltzmann statistics. And by the way, some catalyst forms that are less stable could be more catalytically active in this ensemble. Ensemble sizes and types can strongly depend on the system and the reaction conditions. For example, platinum 8 support on alumina can present many different forms in conditions of dehydrogenation, but only one very stable form in conditions of hydrogenation. In electrocatalysis, support platinum cluster in ORA, for example, can present several different forms, but the most prevalent shape will be strongly depend on the applied voltage. And that means that we have to treat electrons beyond computational hydrogen electrode and include surface charging explicitly as well as the electrolyte. To approach this problem in general, we have to be viewing adsorbates in a ground canonical manner in equilibrium with the reservoir available in the reaction. All of this implies that there are many available active sites and many concurrent reaction mechanisms, not one reaction profile. And these mechanisms altogether are responsible for experimentally observed kinetics, activity, selectivity, and many active sites are responsible for operandospectral signatures. We took this paradigm to many different directions. In thermal catalysis, we were able to explain and predict outcome of the experiment for selectivity of certain catalysts. We looked at the electrode restructuring in operando conditions when we modeled it beyond a computational hydrogen electrode. We showed that fluxional interfaces break scaling relations, and we can use these broken scaling relationships to our advantage in catalyst design. In operando spectroscopy, theory really can help experiment because experiment monitors ensemble average signal dominated by the most stable state of the catalyst. And to figure out which state is actually catalytically active in the ensemble measurement is the role of theory. And some of the very old theories, such as oil ripening theory, needs to undergo an amendment when we talk about strongly fluxional interfaces. Thank you very much.
Presented by Luis Bourbon, University of California, Davis, and the title is Metal Ligand Cooperativity.
My name is Louise Bourbon from the Department of Chemistry at the University of California, Davis. I'm an inorganic organic. My name is Louise Bourbon from the.
Okay. Sorry, guys.
The Department of Chemistry at the University of California, Davis. I'm an inorganic organometallic chemist, and today I'm going to
Streaming it. I don't recommend it. Didn't say well. Exactly. So we're at difficulties. So we're going to move to the next one, and then we're going to circle back to that one at the end. So next one is actually, I believe it's, okay, yeah, Daniela Blanco from Synthetics, and the talk is going to be on leveraging small data for faster and better catalysis.
I'm Daniela Blanco, founder and CEO of Synthetics, where we are leveraging small data for better chemistry. Today, although over 90% of processes are catalytic in nature, we have a huge challenge that comes with the optimization of those catalysts and conditions for the reactions that are taking place. We're dealing with multiple variables and dimensions, nonlinear relationships, codependencies, and much more that make it extremely hard for the human eye and human intuition to keep track of everything that is happening and identify those true optimal catalysts and conditions. AI has come as a tool that is very promising to help us run millions of scenarios and find the true optimal conditions for our process. The problem is that machine learning and AI typically require large amounts of data that we sometimes don't have available. What if I told you that there is no longer the case? At Synthetics, we have developed Synthetics ML, a platform that is designed to bring AI in the hands of all scientists developing new catalytic technologies. You only need to upload an Excel file with information from the experiments that you have run. You configure your target, telling us where you want to go, follow the algorithm suggestions, and you reach your goals up to 15 times faster. The platform is incredibly easy to use, has been developed for scientists by scientists, and in only one click, There's no ML expertise required. You go from the information on your data points from the Excel file to full predictions of how the AI is working, how your system is working, what the optimal conditions are, variable effects, and so much more. To give you an idea of how powerful this is a pilot that we did with a company in Indiana. They were developing a process for a molecule used in fragrances and pharmaceuticals. On their own, they did a total of 39 experiments to map the space and find the optimal behavior. Each point is a different experiment, and they were looking for a bright yellow to maximize the efficiency. The best that they found is this green that you can see here for about 74% efficiency. Then they used our platform. And with only 9 experiments, they were able to find this bright yellow, which they had even originally missed on their initial campaign. The way that it worked is that they started with 5 random experiments that are highlighted in black, and then we guided them, telling them what experiments to run and leading them straight to those optimal conditions. This comes from a prediction of how the entire system is behaving. And it shows how the company was able to go from 39 experiments to only 9, where they got a 74% efficiency. We reached a 93% using the power of AI. This is only one example. We have used this in intermediates for specialty chemicals, crystallization processes, formulations, and much more. Independently of the space, we find a 50 to 95% reduction of time, experiments, and resources required to get to unprecedented performance. We have received a lot of awards and support from many different outlets. You can actually find our TED Talk to get more information about our technology, and we're looking forward to working with you if you're wishing to implement AI to advance the R&D for catalytic processes and implementation. Thank you.
This one is going to be presented by Joseph Gare from Merck, and title is Recognizing Charge More Than Size, Electrostatic Interactions as a Basis for Generality in Asymmetric Catalysis.
Each of these catalytic technologies has transformed the way we approach synthesis, and the tremendous impact of these methods stems in large part from their generality. With this in mind, the most important question in catalytic reaction development today may well be, how can we develop tools like these that are general enough to advance the scope of chemical synthesis? If we consider enhancing generality in asymmetric catalysis, it stands out that the most established strategy for enantioinduction is based on size. Engineering a catalyst's steric profile to control substrate orientation by minimizing steric clash. And an emerging alternative, however, involves orienting substrates with attractive electrostatic interactions. And an essential difference between these approaches is that electrostatic interactions are much less sensitive to changes in interatomic distance. Based on this difference, we envisioned that selectivity achieved by electrostatic interactions would be less sensitive to changes in substrate positioning that arise from changes in substrate size. Therefore, we envisioned that designing catalysts for enantioinduction by electrostatic interactions would serve as a strategy for enhancing generality in asymmetric catalysis. We sought to pursue this concept in SN2 reactions between ion pairs, with hydrogen bond donor catalysts that bind the full charge distribution of the transition state. And if we look at an electrostatic representation of this catalyst, we can see that the 2 hydrogen bond donors, the amide oxygen, and the electron-rich pi face present an internal electric field that's organized about a helical surface forming a chiral environment defined by electrostatic preorganization. So the SN2 reactions that we targeted with this catalyst involved asymmetric anion delivery to cationic oxetanes and azidines. And this catalyst achieves excellent enantioselectivity for bromide delivery to oxetane ions, and this selectivity translates to opening azidines with alkyl chlorides and acid chlorides despite major differences in the steric profiles of these intermediates. High selectivity is also achieved for substrates bearing electronically and sterically varied arenes and heteroarenes, and for non-aromatic substituents including sp3, sp2, and sp hybridized carbons, and several challenging heteroatomic substituents. To wrap up, the electrostatic potential maps of these transition states illustrate how different these reactions are in terms of their steric profiles and how they're unified in the way that they present charge. And from this perspective, we can envision how substrates of widely varying sizes can be engaged with excellent stereo control by electrostatic interactions that persist over varying interatomic distances, Taken together, this work demonstrates that electrostatic interactions can serve as a strategy for enhancing generality and asymmetric catalysis of ionic reactions, and brings us closer to our goal of developing general catalytic technologies to advance chemical synthesis.
This one is presented by Long Shi from Ames National Lab, and title is New Catalytic Mechanisms for Strong Bond Activation Without Transition Metals.
Hello, everyone. My name is Long Chi. I'm a scientist in Ames National Laboratory. Today, I will talk about the breakthrough in my lab using liquid organic hydrogen storage chemicals, LOHCs, for hydrogen storage with metal-free catalysts. Last year, the US government released hydrogen Earthshot goals, seeking to reduce the cost of a clean hydrogen by 80% to $1 per 1 kilogram in 1 decade, so-called 111 goal. The use of a carbon-based organic molecule for hydrogen storage is one of the promising methods for long-duration storage and a long-distance transportation of hydrogen gas. The hydrogen density can reach 5 to 6 weight%, higher than compressed hydrogen. The charge and release of hydrogen requires the use of catalysts to activate covalent linkages, including CH and nitrogen-hydrogen bonds. The existing dehydrogenation catalysts are typically based on precious metals or air-sensitive ones, not suitable for large-scale applications. For this purpose, we have discovered a new type of active sites, metal-free nitrogen-doped carbons. The classic view of nitrogen dopants often illustrates nitrogen atoms are in distance among others. A theory suggests that the formation of isolated nitrogen dopants is more energetically favored. To overcome the challenge, we use a series of diamine precursors for the synthesis. Through a series of catalyst characterization and mechanistic investigation, we have shown that the closely spaced graphene nitrogens can form nitrogen assembly and are active in reversible hydrogen chemisorption even at room temperature. We have studied the catalytic dehydrogenation of tetrahydroquinoline as a representative LHC, and showed that a catalyst can allow quantitative hydrogen release at a wide range of temperatures, even under ambient conditions. Besides, the catalysts show activity over a broad subject scope of nitrogen heterocycles. To conclude, our catalyst is based on carbon materials without use of any platinum group metals and allows the hydrogen release even at room temperature, suitable for large-scale hydrogen applications at mild temperatures. Our work is recently published in Science Advances. My email is shown in the slide. Thank you for your attention.
So the next presentation is given by Hongyan Shen, University of California, Los Angeles. And it's going to be talking about linear pair electrochemical valorization of glycerol enabled by electrophantom process using a stable nickel selenium cathode.
Good morning, everyone. It's my honor to present in this session. I'm Hongyan Shen. I got my PhD with Professor Song Jing at the UW Madison, and I'm currently a postdoc at UCLA. I study electrochemistry and electrocatalysis, so today I will talk about a linear paired strategy for electrochemical upgrading of glycerol into high-value chemicals. Glycerol is a biomass-derived feedstock, and electrochemical valorization of glycerol typically occurs only at the anode. The cathode reaction is typically O2 reduction or hydrogen evolution. More recently, there have been studies that pair CO2 or CO reduction with glycerol oxidation to make carbon-containing value-added chemicals at both the cathode and the anode. However, this requires two different feeds and generate different products respectively. So how about having only one feed, which is glycerol, and making the same oxidation products from glycerol both at the cathode and the anode? This is actually doable because there are certain cathode reactions that can generate oxidative species in the solution. For example, O2 can be reduced to H2O2 in a 2-electron pathway, and H2O2 can further undergo the iron 2 plus mediated electrophantom process to generate the highly oxidative hydroxyl radical. In this case, glycerol can not only be oxidized directly at the anode, but also can be oxidized near the cathode by this hydroxyl radical in a so-called linear paired fashion. Electrophoton process requires the cathode to be acid stable, selective for 2-electron ORR, and stable in the presence of oxidants such as H2O2 and hydroxyl radical. We identified nickel diselenide as a promising cathode. Our computations elucidates its selectivity and stability, and our experiments further confirm nickel diselenide can indeed accumulate H2O2 and exhibits suppressed catalyst leaching. There are challenges in controlling the product selectivity for glycerolization because it can be oxidized sequentially into various C3, C2, and C1 products. We want to keep the glycerol oxidation in early stages to access more C3 products that have higher values. We carefully tune the iron 2+ concentration to control the production rate of hydroxyl radical from electrophoton to access high C3 product selectivity. Finally, we demonstrate this linear paired process in an H cell to produce mainly C3 oxidation products from glycerol, both at the nickel diselenide cathode and the PT anode. Further device engineering in flow cells could be helpful for accessing better product selectivity by controlling the mass transport. Nevertheless, we're excited about this linear paired strategy that could be generalizable for oxidizing a variety of biomass-derived feedstocks. Thank you for listening.
One is going to be presented by Yogesh Surendrana, MIT, unifying disparate branches of catalysis science.
I'm Yogi Swainarnath. I'm a professor in chemistry and chemical engineering at MIT. I'm excited to tell you about the opportunities for unifying disparate branches of catalysis science. Catalysis science is historically developed along a number of subdisciplinary buckets. They often revolve around the type of catalyst that's chosen, heterogeneous, molecular, or biological, and they further bifurcate around the mode of energy input: thermochemical, electrochemical, or photochemical. Each of these modes of input and each of these types of catalysts are often paired together, and in many situations, they can carry out common reactivity and common transformations, often by common elementary reaction steps. So we envision that there's enormous opportunity to integrate across these disciplinary sub-buckets and these different modes of energy input to expose new reactions, new materials, and new catalysis. We began by bridging molecular and heterogeneous electrocatalysis. We recognized that in a molecule, because of the discrete electronic states and the low coupling to an electrode, what you got was a stepwise reaction in which electron transfer to the molecule was then followed by a separate step for substrate bond activation. In contrast, the active sites of a heterogeneous surface are strongly coupled to the band electronic states, and so electron redistribution and substrate activation are actually concerted. This leads to an energetic benefit, but you lose the ability to tune at a molecular level the active site. We identified ways to actually bridge the benefits of both molecular and heterogeneous catalysis by making a class of catalysts called graphite conjugated catalysts. Here we take a molecular site and connect it to a graphitic carbon surface through a strongly coupled aromatic linkage. And we showed that these graphite conjugated catalysts display the conserved reactivity of heterogeneous surfaces while also having the tunability of molecules. We were able to then develop molecular scaling relationships and proton-coupled electron transfer using this platform and expose reactivity for CO2 reduction, hydrogen generation, O2 reduction on different graphite conjugated systems. We recently showed that you don't need this fancy linkage to be able to support metal-like reactivity, provided that your active site is able to strongly adsorb to the surface and display the ability to be polarized by the change in potential of the electrode. We also, in parallel, have been examining how to connect thermochemical and electrochemical catalysis. Many challenges in catalysis science now involve liquid phase catalysis. Unlike gas-solid catalysis, liquids can stabilize charge separation. So we envisioned that the electrochemical potential of the surface may change during catalysis. And if we could measure that value, we could use it as a descriptor that could cut across both thermochemical and electrochemical catalysis. By doing that in the context of aerobic oxidation, we learned that many classes of aerobic oxidation reactions actually proceed by coupled electrochemical half reactions. And we use the electrochemical data to predict the thermochemical reaction rate across a remarkable array of substrates, materials, and catalyst types. We further showed that nonpolar reactions like olefin hydrogenation could be further tuned by superimposing an electrochemical polarization of the interface, and that there is a systematic scaling between the potential and the reactivity. I hope I've shown you the opportunities for being able to bridge across different modes of catalysis.
Next presentation will be given by Jenny Yang from the University of California in Irvine. The title is Installing Internal Electric Fields at Active Sites Using Proximal Cations.
My name is Jenny Yang. I'm a professor in chemistry at the University of California, Irvine, and I will talk very briefly about some of the work that we're doing in installing electric fields at catalytic active sites using proximal cations. So when we think about trying to understand reactivity and design catalysts for specific reactions, we often think that what we're trying to do is really modify an energy landscape for a reaction. One of the most common ways that we can do this using a non-covalent interaction is, for example, with steric repulsion. And we do this so much that it's pretty intuitive to use a steric to modify an interaction. Another example, for example, is hydrogen bonding. But one that I think that we use less often is electrostatic interactions. And so you can think about reactants, products, or transition states all having a dipole moment associated with them. And these can change in energy depending on the relationship with an electric field. And that can include, for example, accelerating reactivity by lowering a transition state energy, or increasing product selectivity by modifying competitive reaction pathways for a specific catalyst. The way that we try to induce this in our own catalytic system is by using proximal cations. We often use this ligand framework, which is a saline ligand, which can encapsulate a redox active metal. And then we have a crown moiety, which can encapsulate a redox inactive metal, for example, an alkali or alkaline metal. And this way we can basically introduce charge into this cavity. And we've looked at thermochemical properties as a relationship with this charge. So for example, by having charge +0, +1, +2 to +3, you can change the redox potential by over 700 millivolts and the pKa by over 9 units for a hydrogen atom transfer type reaction. We've also explored some reactivity with these systems. This is one example for aerobic CH oxidation, catalysis. And we found that the presence of having these cations present allows oxidation, CH oxidation reactions as aerobic oxidation at milder potentials that would otherwise be possible by using more traditional inductive effects, which has a different impact on the electronic structure of the metal ion. Another example of the effect these cations have on reactivity is shown here, where we use that manganese nitride reaction, and we looked at the coupling of the nitride to make the N triple bond. And we find that the presence of the cations basically result in an inverse linear free energy relationship for this coupling reaction, so that essentially as you get to manganese nitrides that are more oxidizing, the reaction actually slows down. And so these are just a few of the reactions that we believe are influenced by having this local electric field induced by these proximal cations.
Right, so the next one is going to be presented by Peter Zhang from Boston College. The title is Metalloradical Catalysis for Stereoselective Radical Reactions.
Hi, everybody. My name is Peter Zhang. I'm a professor of chemistry at Boston College. I want to take this opportunity to introduce you to a new type of catalysis we coined as a metalloradical catalysis. The idea behind a metalloradical catalysis is trying to catalyze organic transformation via homolytic radical reaction. We would like to use metalloradical catalysis to control reactivity and the selectivity of one electron homolytic radical reaction. Here is a schematic presentation of a metalloradical catalysis. In metalloradical catalysis, the open shell transition metal complex serves as a catalysis to activate substrate A through one electron homolytic radical reaction. During the metalloradical activation step, there is translocation of radical characters from metal center to the organic fragment. Depends on the nature of A molecule, we can generate alpha metal alkyl radicals, or alpha metal amino radicals, or alpha metal oxyl radicals. Those organic radicals, which is supported by matter, their reactivity and selectivity can be controlled by the matter center in conjugation with a ligand. Despite the stability, those metal support organic radicals still have rich reactivity, can undergo common radical reaction, such as radical addition, atom abstraction, to generate new metal support radical intermediates. We have demonstrated two radical reactions allowed us to turn over metallo-radical catalysis. One of it is radical substitution, the other is radical substitution to cleave metal carbon, metal nitrogen, or metal oxygen bond to deliver product C while regenerate metal center radicals. By doing so, we have demonstrated metallo-radical catalysis can be applied for a variety of important organic transformation through stepwise radical mechanism. The application include radical olefin cyclopronation, olefin radical azotronation, radical CH amination, and radical CH alkylation. Thank you.
As promised, we're going to circle back to the one that we missed. That's the one presented by Louis Bourbon, University of California, Davis, and the title is Metal Ligand Cooperativity.
My name is Louise Bourbon from the Department of Chemistry at the University of California, Davis. I'm an inorganic organometallic chemist, and today I'm going to tell you about our work designing new ligand frameworks that can support aluminum and other group 13 metals such as gallium so that we can get covalency and cooperative activation to look at catalytic reactions, the types of things we might usually think of doing with transition metals. So why group 13? Well, it's very abundant in the Earth's crust. It's mined domestically. It's very inexpensive. And from a chemistry standpoint, it's very underexplored. There's so much new things we could do with aluminum if we just put in the time to designing and finding the correct ligands and developing their chemistry. So what's unique about this chemistry? Aluminum has valence p orbitals, and so they make good covalent interactions with the nitrogen and oxygen donors on ligands. Redox active ligands in particular, where we can put electrons into the framework, donate into that aluminum p orbital you see at the top here, so we get metalloaromaticity, and this leads to really interesting transformations. So far, my lab has developed transfer hydrogenation chemistry, acceptorless dehydrogenation chemistry of amines, which is oxidation chemistry, and looked at some of the fundamental bond breaking and making elementary steps, which are listed at the bottom of the slide here. For just a couple examples of those processes I have on this slide here, on the right, you see the NH activation of an aniline. The ligand accepts the proton, the metal accepts the conjugate base, and after elimination of hydrogen, you can get these square planar complexes back, and you can see hydrogenative coupling, CN coupling from anilines also in the bottom right there. And this is reminiscent of a lot of the ruthenium chemistry that was done by Milstein and co-workers. In another example here on the left, you see formic acid dehydrogenation, which is very fast, very efficient, on par with some of the iridium chemistry that's been reported. And then on the right of this slide, you see transfer hydrogenation chemistry, where we get out-of-sphere hydride transfer from donors to acceptors. And so there's a lot of scope here for ligand design and for applying these fundamental reaction steps into other types of chemistry, both to discover new chemistry and to replace some of the precious metal catalysis that we're used to. Thank you.
Thank you so much for the online presenters. And now we move to the last 4 presentations that are going to be in person. The first one is going to be given by Samay Garg, Columbia University. And title is Tandem Catalysis for Rapid Decarbonization of Chemical Manufacturing. So for the speakers, we're going to have this very nice device here. So if you're in green, you're okay. You're going to have 30 seconds before you finish in this one. And if you keep talking, you get the red one, and you get zapped with electricity. Right? Right. Please go ahead.
How do I advance the slides? Okay. Thank you. My talk today is a brief perspective on how tandem catalytic processes will drive rapid decarbonization of chemical manufacturing. So the chemical industry is inherently tied to fossil fuels for both energy and chemical feedstocks for thermochemical reactions. Chemical manufacturing almost always starts with natural gas or crude oil, which are extracted from the earth and refined, converted, and upgraded by various processes to produce thousands of chemical products, which are integral to our modern society. Thus, the chemical sector must very quickly adapt to using renewable energy and sustainable feedstocks, while still increasing production volumes if we hope to decrease fossil fuel extraction and meet our climate goals. To make this problem more tractable, we should focus on where emissions are highest, and you can trace the chemical manufacturing chain back to this group of the 17 highest volume chemicals, which count for about 75% of chemical sector emissions. Looking at the simplified diagram of material flows during chemical processing, you might notice that this core group of olefins, BTEX hydrocarbons, ammonia, and methanol are used as precursors for the rest of the supply chain and account for over half of chemical sector emissions. Thus, initial decarbonization efforts should focus on these 17 chemicals and especially on the 5 core building blocks. We envision a tandem catalytic paradigm as the most efficient way to rapidly decarbonize and reduce chemical sector emissions. Sustainable precursors can be electrochemically refined into a group of simple products, which can then be upgraded and converted into the core building blocks and high volume chemicals that I just mentioned. Of course, all of this is predicated on the assumption that we have sufficient renewable electrons to power these processes. Electrochemical CO2 reduction is a good example of why this tandem approach is beneficial. Coupling electrochemical CO2 reduction with a downstream process which is able to use simple products in a mixed feed obviates many of the barriers to real-world implementation of these products. For example, hydrogen is typically an undesired side product, but carbon monoxide and hydrogen is syngas, which is a useful feed for many well-established thermochemical processes. My work has demonstrated transition metal nitride-supported catalysts as an alternative to bimetallic catalysts for controlling the carbon monoxide to hydrogen ratio with this coupling in mind. And the second step is the reactions which are able to proceed at elevated temperatures but ambient pressure because they're much more well suited to electric heating. And these reactions also need to be compatible with mixed feedstocks. One recent example from our group is the ethylene hydroformylation, wherein we use rhodium-based catalysts to convert a mixture of ethylene and syngas to C3 oxygenates downstream of an electrochemical CO2 reduction reactor. We have also used gallium-modified zeolite ZSM5 to catalyze CO2-assisted aromatization of ethylene to produce BTEX aromatics with high conversion and selectivity. This was a very quick talk, and I've glossed over a lot of details, so I'll leave you with some closing thoughts. The quickest path to decarbonizing the chemical industry is implementing sustainably fed electrochemical processes, which can be coupled with a combination of new and existing thermochemical processes to produce high-volume chemicals. This is not to say that other sustainable catalytic options or one-pot solutions cannot eventually meet the requirements of industrial-scale chemical synthesis. However, thermochemical processes simply have a several decades-long head start, so we should use this knowledge to our advantage while we give other techniques the time to bridge the gap. Finally, divorcing chemical manufacturing from fossil fuel feeds will enable the growth of a distributed chemical industry, which can more quickly respond to advances in sustainable catalysis. And thank you for listening.
We're moving to the next one by Randall's Northwestern University, data-driven computational discovery of metal organic framework catalysis.
So I think this audience is familiar with MOFs, and we now have MOFs that are stable enough you can do interesting catalysis. And MOFs are nice because they can combine the best features of different classes of catalysts. So for example, they have these well-defined metal sites that we can tune by changing the metal and changing the ligands around them. But at the same time, they're solid materials, and so they have a lot of the advantages of heterogeneous catalysis. We can also think about modifying the cavities around these active sites, reminiscent of how enzymes function. And MOFs are also a really nice platform for computation-driven catalysis. They're crystalline, so they have these well-defined active sites. They're tunable, and there are large databases of known and hypothetical MOF structures. So in our work, we have two goals. First, to identify promising candidates, but I think equally importantly, to better understand how they perform. In some of our work, we've been looking at oxidation of alkanes. So we have these spatially isolated metal sites within the inorganic nodes of the MOF, and the reaction mechanism is shown there. And there are three key steps. First, forming the metal oxo. We're using something like N2O or hydrogen peroxide. The oxo then has to be able to abstract hydrogen from the alkane. That then pretty readily forms methanol. And then the third step is desorbing the methanol. So using density functional theory, we looked at about 60 MOFs for this reaction. And we found an interesting, nearly linear relationship between the energy for activating the CH bond versus the thermodynamics of forming the oxo. And there are interesting periodic trends. So at one end of the periodic table, it's difficult to form the oxo, but if you could, they'd be super catalysts. At the other end, you can readily form the oxo, but they're not very reactive. But there are materials in the middle, in this sweet spot, where we find things like iron, which is known to oxidize ethane to ethanol, but also copper and cobalt, which might be interesting candidates going forward. We've also looked at oxidation of propane, either to propanol or to propylene with oxidative dehydrogenation. And here we're looking at a very specific class of MOFs with the metal node shown there, which has two irons and then another metal that can be varied. And again, we see this trade-off in the blue versus the red in the middle between forming the oxo versus activating the CH bond. And on the right, we looked at those four different compositions of the metal node, and the predictions from the DFT were validated then later by our experimental colleagues, showing that we can tune the activity by changing the composition of these metal nodes.
The next one is going to be presented by Emily Sprague-Klein from Brown University. Did I mention your last name okay?
Yes, Sprague-Klein.
So I was working on it. So, legally induced chemical structure dynamics in transition metal oxides for photocatalysis.
Good morning. As mentioned, my name is Emily Sprague-Klein. I'm a new assistant professor of chemistry at Brown University, and I'm very excited to be here today to talk a bit about some key results related to light-driven water splitting catalysis. So a lot of my research interests involve developing a mechanistic understanding of how to utilize visible light to lower activation energies for the onset of catalysis. So in this particular work here that was published recently in ACS Energy Letters, we were focusing on water splitting electrocatalyst known as CoPI. It's a phosphated cobalt oxide with molecular scale domains. This is a solar harvesting material that is typically found in the three-layer photovoltaic, also known as artificial leaves. And the novel approach that we took here was to utilize a dual wavelength excitation approach of this electrochemical reactor cell. And what we noticed was whenever we shined differing wavelengths of light on the reactor cell, we were able to induce a transient anodic and also a cathodic current, depending on if we used red light versus blue light. And so I think this presents very exciting opportunities to dynamically couple charge transfer resonances of the material with redox catalytic activity. In particular, we can think of this in terms of an atomic description of material where we can utilize light to mimic aspects of the catalytic OER cycle by, say, exciting an electron from a cobalt atom to a nearby oxo ligand, and by creating this CO3 dot species form the precursor for the release of diatomic oxygen. Furthermore, if we look at this photoelectrochemical type of approach on the ultra-fast timescale, we use techniques such as transient absorption to look at the underlying electronic and structural behavior. We notice that if we look at the kinetic trace of the cobalt-3 spectral peak, what we can derive from this is extracting 3 differing lifetimes that correspond to things like exciton formation, recombination, and most importantly, the presence of this long-lived charge trapped species that correlates directly with OER functionality on long timescales. So I think this is a very exciting opportunity to bridge the gap between ultra-fast electronic and structure dynamics with chemistry, particularly redox catalysis on water splitting timescales. So thank you very much.
Right, so that's the last presentation of the whole workshop. It's going to be given by Sarah Toy from Johns Hopkins University. Title is Novel Molecular Strategies to Modulate the Electrode-Electrolyte Interface in Heterogeneous Electrocatalysis.
Right, no pressure. Okay, here we go. Oh, sorry. So I'm really excited to be here to tell you about one-distant catalysis, in particular in using molecular strategies to really tailor electrochemical interfaces for activating and forming new bonds. One example of this in my group has been shown in using things like molecular additives, particularly amphiphilic molecular additives that can accumulate at the electrode interface for carbon dioxide reduction. You'll see here that the cationic charged surfactant species would then accumulate at the negatively biased electrode that then creates this hydrophobic interface. What we think is happening is that this enhances CO2 reduction to CO and formate by depleting proton sources at the interfaces that would otherwise be used for hydrogen evolution reaction. Now you'll see that by the in situ IR on the left here, on my left, that there's a negatively going band in water in the presence of this amphiphilic surfactant. Because I only have 3 minutes, I'm going to direct you to this account that was published earlier this year in 2022 that talks a lot about this interfacial engineering. But what I'm really excited to tell you about today is really a new direction in my group in electrochemical urea formation. The goal is to really replace this Bosch-Weiser process, which occurs at high temperature, high pressure, to make urea, which is used very commercially for resins and agricultural fertilizers. The Bosch-Weiser process couples ammonia, which then comes from Haber-Bosch, with CO2 to form this urea. But what we're trying to do is replace this with electrochemical CN coupling that can occur under fairly ambient and modest conditions. We're going to couple 2 waste products, so I'm glad Will came before me, in CO2 and nitrate in wastewater to then make urea formally. What we've done is that we've used gold as a really nice platform to understand the fundamentals of this reaction. On the left here, you see that we get fairly modest Faraday efficiency or selectivity and current densities or activity. But what's nice is that the surface enhancing properties of gold allows us to use in situ IR to look at bound CN intermediates. And we've been able to observe that bound CO and interfacial nitrite species are really important in dictating the selectivity for urea production. But even more excitingly is this slide here. We've shown that under controlled potential electrolysis, meaning one potential, we get okay activity and selectivity. When we start pulsing the voltage, we actually get much better activity. And this is a strategy that Susanna had alluded earlier. Dynamic pulsing allows us to actually increase our Faraday efficiency up to 50 to 60%, as well as increase our activity by 5 times. We think the reason why this happens is that by kind of pulsing our potential cathodically and anotically, we end up having enhanced nitrate transport to the interface that then allows for activity to turn over. And this is really exciting. It means that we could use a variety of techniques, both molecular and potential ramping, to really tune this interface. And so we're really excited about this. And I'll end on an acknowledgement slide. This work was primarily funded by DOE.
Thank you. So let's all actually thank all of our speakers for this session. They gave very nice presentations today. So as I mentioned before, we're going to take the next few minutes before we close, so actually to look into a reflection of what we've heard during this Vistas session. And let me remind the people in the virtual audience that they can actually raise the hand if they want to make any comments or suggestions or questions. And for the audience here, they can use the phone that is actually over there. I believe we have okay, so we have the list of all the topics that we covered during this session, and it's actually very broad, as you can see. But one of the things that I take out of all this, I actually a couple of notes here. So one of the things for me that actually was very interesting, that seems to be the theme of the whole workshop, is actually a few things like integration. It is indeed that catalysis is becoming a real multidisciplinary discipline. And we need to unify some of these themes to actually tackle these grand challenge problems that we're facing and we're going to continue facing in the future. We also saw examples of novel applications, like rapid decarbonization, glycerol valorization. So essentially the theme here is actually catalysis is becoming just not a research subject in universities. It actually has a connection with impact in the society and our local economy. So we're looking more into that. So I'm happy to see that that we've seen a lot of that nowadays, and we saw a lot of examples through the whole workshop. And something that is actually, I'm a theoretician, so I'm really love to see this theme about data, machine learning, and artificial intelligence. It is becoming clear that data is becoming really complicated, and you need better data analysis. And I will actually say, this is a plug on the things that I do. It's not only developing these algorithms, it's also the validation of these algorithms. The current status of this machine learning in science is people tend to use the things when they actually can predict some numbers. And sometimes they don't really care about the validation of these models. Hence, the reliability of these approaches sometimes really get trouble because we don't do a good job of validating. But to validate these methods, you need very good data. That's why this combination of machine learning approaches with the experiments that people are doing in catalysis, I think is actually very, very good and very timely. The other thing that as well as a physical chemist I really appreciated was some of the talks focusing on ways of actually changing the energetics of the potential near surface to actually to provide you real products, accelerate the production of whatever you want, changing the potential near surface. This is something that actually requires more refined thinking and modeling and also measurement techniques that will allow people to actually do this a lot. So I really enjoy the photocatalysis piece, which is another way of actually looking at some of these intermediates. So with that, I think I will ask you also, Linda is gonna pass around some post-it notes just in case that you have any comments or epiphanies, again, as I said. And but just to break the ice, so I have a list of 4 questions that the committee actually came up with to actually break the ice to initiate our conversation. And I'm sorry I didn't put it on the slide. But the first question is, the topics that we covered during the Vistas, are there enough? Or do we miss anything? You would like to see something else in the future? And is that, what would that be? So what other opportunities you see in all this space of catalysis moving forward in the next few years, right? So this is something that we always ask. The other is, what are the most promising and exciting things according to your experience and what you've heard today and maybe yesterday in the area of catalysis, right? And one of the things that might actually be important for, especially for young scientists and students, what should we be focusing on, the researchers in this area? What are the focus? Okay, catalysis is very broad, as you all know, and so what are the areas based on the priorities of society and so on and so forth? What are the kind of things that we should be focusing on, or should we just actually leave it as it is? So those are 4 questions, and but obviously you can, you're welcome to actually make any comments. And with that, I stop talking, and we'll listen to you guys.
Hi, Karen Goldberg from the University of Pennsylvania. What has struck me in this meeting is really how much progress we can make with chemists and engineers working together. It was just wonderful to have us all at the same meeting, speaking the same language that we can understand. And I hope we can keep doing this moving forward.
Lunch break yesterday, we had a very lively conversation about that, some of us. And so it's actually important we have to recognize that sometimes we don't speak the same language, chemists and engineers, and we need to actually make an effort, because as I said, this is becoming a real multidisciplinary issue, right? And so we need to actually work together. That's a very good one.
Hi. So just to be a little bit more clear about the instructions with the Post-it notes for those in the room and for those online, the chat box, Eric, if we can activate the chat box, that can be your form of a Post-it. So the idea is for you, if you need a pen, please let us know, but to put any key takeaway messages that you heard in these talks that may inspire you when you leave this workshop today. And if you would like to share, please feel free to share.
So do we have any comments from the online? No, we're gonna have to zap these people. Next one.
Hi, Carlos. So I wanted to build, this is Mary Kirchhoff, retired from ACS. I wanted to build off Karen's comments, which we talked about a little bit earlier too. Her point is spot on about how the chemists and engineers interactions has just been fantastic throughout this workshop. However, I still see education lagging behind where we need to be. Chemical engineers, as part of their education, take chemistry. The reverse is not true. Chemists do not take chemical engineering. And I think there's still huge gaps in the curriculum in terms of things like sustainability, AI, machine learning, data science. I know industry has cited this gap in education. So I know that's another huge project for the academies to undertake, but really addressing the education of chemists and chemical engineers, making those recommendations that can really help our 2 disciplines work together more seamlessly to break down these barriers and foster that integration, I think is critically important going forward. Thank you.
Actually, I guess the question that I have for the audience is, okay, so we actually, Mary was talking about the educational piece. What else? I mean, for the professionals that are actually already working, how do we actually bring these 2 people, the kind of people together, the engineers and the scientists working in catalysis? Is it something that should happen organically, or should be actually structured, right? So maybe societies, maybe the federal government should actually, the companies, I don't know. So maybe that's something that we need to discuss as well, because that's very, very important.
Hi, I'm Franz Geiger from Northwestern University. One thing that is striking is how much surface chemistry there's involved in the processes that we've heard about, and how little surface-specific experimental approaches exist that have the capability of going beyond the vacuum gap. So condensed matter interfaces, be it liquid-liquid, liquid-solid, or even solid-solid interfaces are really not prone to interrogation by any by spectroscopic means. And we've heard just a little bit about it in this workshop, but I think it demonstrates that we really need to push for X-ray eyes underwater, right? I want to see chloride at the interface versus cyanide. I want to see the presence of species for which I cannot do vibrational spectroscopy, but I also want to learn about the solvents, because those are often the source for the electrons that we're using. Think about the oxygen evolution reaction, right? No one cares about the oxygen. We want the electrons, and those come out of water's oxygen atom. But you can't probe it because it's a strong absorber problem. And so I think there's a huge space for improvement from the fundamental perspective of new technologies and spectroscopies and microscopies under operando. So we learn, we go beyond the current approach of understanding a lot of these conversions, which is correlation. And as a chemist, I really like to see causality, and I'm missing that in the field.
Probably add to that we need more better ways of actually experimentally probing some of these intermediates so we can actually get a better sense for these mechanisms. At the moment, nobody's going to get the real mechanism from anything, but at the moment it's just a trial and error kind of approach, and mostly because we don't have enough information about some of these intermediates. Now, there are intermediates that are so reactive and the lifetimes are so small that it's impossible almost to virtually to get in. But there are others that we could probably do a better job if we actually come up with this new set of observations and techniques to actually look into those. Next one.
Sarah Toy, Johns Hopkins University. So echoing Mary and Karen's discussion, I think reactor design is a maybe less appreciated field and maybe less sexy, but I think that's really where we need to be. I think chemists need to take reactor designs, chemical engineers like Will need to teach me how to do that well. I think that's really critical. The other piece I was going to mention is that I think it's pretty clear from Will and LaShonda's talk that public outreach is really important, not just in plastic recycling and waste treatment, but in kind of all areas of catalysis. And I feel like that's something we might need to do, like a public health campaign, but in energy. And I think that's really necessary for moving our field forward.
So I'll preface this with one of my great joys in life is arguing with Franz Geiger over a beer. But I will push back a little bit on his comment. We did see the slide from Bob Mahan that showed where the heyday of catalysts were and where our understanding is going. And the thing that is true is, in spite of all the operando and all the other things, our pace of new discovery has not really kept up with our understanding. So to some degree, we do have to question. I mean, I'm still waiting for that one catalyst that somebody from first principles designed and then went and demonstrated, as opposed to what Eve talked about, where you have potentially more serendipitous discovery. So I guess I want to put a plug in for what I believe he said, which is get smart people to go in the lab and play a lot more. And
good point. So the other thing that I was going to ask, I was going to mention, so the business of scalability, right? So that's always comes across when we have conversations between fundamental scientists and people that work in industry. So that's another thing that we need to actually, and it was mentioned many times throughout the workshop. Yeah, we need to actually, when it's like a systems approach, we need to actually understand. So if we're going to do this, is it really scalable? So the proof of concept is important, but always we need to keep in mind that there is an impact behind all that, right? To actually, obviously, fundamental research and innovation actually doesn't follow the same pace that the bottom line. But I think I saw discussions during this workshop that actually were aiming at, well, maybe we should actually have this conversation more often and see if we can actually design these experiments and all this science from the bottom up.
Actually,
So hold on. So we do have two people from the virtual world. Let's go with Anastasia Alessandrova.
Yes, hi, thank you. I wanted to actually follow up on Franz's comment, which I think is very important. And from my point of view as theorist, where we see that many different active sites and many different mechanisms can be in operation simultaneously at this complicated heterogeneous interfaces, it would be really important to develop experimental techniques that could separate out active sites from not active sites, metastable rare sites that are doing all the catalysis and going beyond ensemble average measurements.
Yeah, thank you very much. Next one.
Yeah, let me add to the comment that you just made before, Anastasia. Scalability, I think, is a very important factor. So are other practical issues under which we need to operate. So if we want to work with plastics waste, we need to at least pay some attention to the rheology of the feedstock, which is different from syngas. We need to think about what happens to my catalysts under reaction conditions. Are they stable? Can I regenerate them? Not every kind of deactivation is equally detrimental in terms of whether I can ultimately use the catalyst along these lines for a process. And there are many more of these issues. And so I think it would be important for us as a society to come together and formulate research needs to address many of these issues. And we can still do good fundamental science once we're aware of these, just more targeted.
I agree with that. So how do you see that happening? How would you actually bring all this together?
I mean, one step in that direction would be to find funding mechanisms where if you want to work on practicalities like this, it's not the kind of proposal that's reviewed above average, but ultimately not the most exciting one, and only one or two get funded in a given panel. So it would be important to break that.
Right, so we'll take one from the online again. Pam Chu.
So hi, this is Pam Chu from NIST. This has been really a wonderful workshop. It's really emphasized the large diversity of problems that and opportunities that we have to really move the needle forward on some really major societal problems. I think one of the things that was touched on is the need for collaboration and coordination of research, and a couple of comments that have really started coming up and evolving recently, especially Carson's comment about how do we bring things together to really identify key problems, and the need for developing more collaboration between industry and academia has been touched on in some of the discussions. So one of the things that I find from my own experience is that one of the things that worked pretty well, I think, in the 90s when we were really trying to accelerate research in the semiconductor industry, is that there was an industry roadmap that was developed. And perhaps this already exists, but it might be a way of identifying kind of really the key priorities and knowledge gaps that need to be addressed, and that might be another way of helping coordinate and providing some sort of map that we all could look at and say, oh, okay, my expertise, or I can leverage my expertise and contribute it in this area. Identify specific areas that we could leverage our expertise that match what industry might need. So that's just a suggestion.
Thank you, Pam. Suzanne?
Well, Pam stole some of my thunder because because I was going to say that I think we need better venues for conversation, and we need to tackle this problem of why translation of academic research into industry has been so underwhelming in the past few decades. I think we need to ask more specifically industry, what is it that they think they need from us? And they need to communicate better to us how we can participate in this whole-scale societal transformation, which we all think is coming. And if we're not talking to each other, that is going to be much slower than it really should be. My second point is about sustainability and a plea to the whole community to start thinking about how we can make these claims in a more scholarly, rigorous, meaningful way, that slapping the label of sustainability on absolutely everything because it just, it looks good, is actually not serving the community and helping to move this forward. And so we need to think about how to actually demonstrate and rigorously describe what contribution to sustainability really means in our field.
I will probably say that one of the things that we need to actually probably rethink is the way we sell sustainability. And so, it cannot just be the moral issue that obviously is important, the environmental impact and so on, but it has to have also the economical impact, right? So is it really economically impactful for companies to actually really take a look at these sustainability issues very seriously? And I think that's important. It's happening also with environmental sciences and climate, for instance, right? So you have to actually look at the bottom line as well. So that's an important conversation now. So let me take one from the online. Anna?
Yeah, hi everyone. I had a comment also regarding sustainability, but more about sustainability of academia itself. So it's following up on the point that Susanna brought up yesterday. So I haven't been here for that long. I have seen so many waves already. So I don't think that's sustainable, and I think it would be better if everybody could focus on a couple of points and not changing the topic that we are focusing every 2 or 3 years, right? Whatever funding is. So it's like, it's not sustainable going deep in important problems if we need to change and read the literature every 2 or 3 years, right? Just to be able to follow up on that, right? So it's kind of hard. So that's not sustainable, I think. And also it's not sustainable all the things that we need to do, right? From the point of academia that are not focusing on research. So how do we all become together to discuss all these important points if we are doing so many things at the same time? So if we really want to do research, we should be doing research, right? And we should really have these opportunities to talk together, to think about different problems, but not changing the topic every 2 or 3 years, right? Because it's kind of difficult to go deep and try to solve problems if we are just following these waves, right, every time. So just my 2 cents. And thank you very much for organizing this. It has been great. Thank you.
Thank you so much.
Yeah, thanks. This was a really nice workshop. And I like the different perspectives that came to the table here from many different fields of academia and from different federal agencies, from industry. Couple things that really resonate with me is, we had something at NSF a while back called Infuse, which was innovations, at the food, energy, water nexus, or the nexus thereof, I guess that was the end. And we had a nitrogen cycle workshop and a phosphorus cycle workshop, water cycle workshop. And this whole interest has been rejuvenated with what I heard today, particularly the nitrogen cycle that Will's talk was very inspiring. We often think about, biorenewable feedstocks, things like that, but at least I don't. I'm going to walk away from this meeting thinking differently about feedstocks and thinking about waste is misnomer. And thinking about circularity that way, certainly with respect to nitrogen. I think phosphorus as well. Now I'm really wondering. I'm hearing about urine as a source of ammonia. I'm thinking urea. Then I got to hear about urea. I'm thinking, well, carbamyl phosphate. That's what you really want, isn't it? And then you'd have nitrogen and phosphorus. I don't know if you want them stoichiometrically, but all of this kind of rethinking about circularity was really inspired by this workshop. So a different way of thinking about circularity. And I think there are a lot of opportunities there. Carbon cycle looks like really rough. LaShonda talked about dialing in plastics so that, those triangles maybe have a little more chemical meaning. I think we've got a lot of challenges there. And finally, on energy, electrocatalysis and redox potential looms large from what a lot of the talks we heard today, and tuning that well. And of course, electrons aren't free. So solar, coordinating better, either directly driving redox chemistry through captured solar. And we heard a little bit about the water splitting, the tuning the water splitting just now, I think is untapped territory. Solar, we got to capture solar more efficiently, and electrons will be part of it for sure. This reminds me, Mark and I were talking in the break yesterday about how nature does so well with solar in essentially generating redox equivalents and capturing CO2 at the same time and making glucose and a lot of complex things. Why can't we emulate that better? And Mark pointed out how distributed that is and how different that is from a menu. And I think that's a great point.
and somehow, solving that problem, how capturing solar more efficiently and taking it from a distributed process to a concentrated plant process. These are grand challenges, but I think the electrochemistry underlies what you're doing in the middle there, and we heard inspiring work in that area.
Thank you so much. We have one also online, Jared.
Oh, hi. Can you hear me?
Yes.
Yeah, Abdul Jire here from Texas A&M. So this is more like maybe to initiate a discussion on something. There's been a lot of talk about integration and collaboration, specifically with industry, and one thing I think about as a diaspora scholar, and I think about how this collaboration can go beyond what we have discussed here so far, and I think about how we can tap into untapped potential in some other places in the world beyond what we've been discussing so far. So what made me think about that is just a couple of weeks ago I was in Nairobi for the National Academic of Science Frontier with the African Academic of Science, and it was very nice to see how the inclusion of science, how the diversity in science can advance our knowledge and the way we think about things and how we approach problems from different perspectives, and how we can complement each other's really strength in advancing, not only tackling the challenges that we have discussed here today, but also thinking about the future and how we can work together. And so I would like to put that in discussion here, and I would like to know what are some of the challenges that really prevent us from coming together and moving forward in the right direction and tackling, because the problem that we have discussed here, for example, wastewater treatment by weight, etc. These are problems that actually, particularly in Africa, that people face, and predominantly. So what are some of the things that we can do that we are not doing that we could do better and that will help us to move in the right direction?
Thank you.
So,
Rob Malechko from Michigan State. So I think when Linda asked, what are the takeaways from this workshop? One of the things that I took away is that if we did this 25 years ago, I don't think we would have had this common thread of sustainability throughout this workshop. And I don't disagree that there can be more coordination and more focus, but I'll just leave it. I think that's a good thing.
Yeah, that's the bright side of the whole thing. So it is true. Any other comments? One more here.
Yeah, good morning, Eve Hermans, UW Madison. So let me try to offer a perspective on how we bring all these different communities together. So my back is hurting, sorry. So at UW Madison, I started teaching a course which is called Principles of Chemical Engineering for Chemists, introducing scientists to concepts like energy and mass balance, reactor design, that at least have the basic foundation and the vocabulary to interact with engineers. The second course that I would like to mention is Industrial Chemistry and Business Fundamentals. And I co-teach this with William Banholzer, who used to be the CTO of Dow. And so the students very much appreciate that they see where all the things they've learned in their curriculum is actually applied, and what are bottlenecks in a certain value chain, and how would you assess potential alternatives.
Any other comment? Questions? Anybody online? All right, so if not, I think we're ready to close. And let me follow my script here. I'd like to thank everybody for attending, people online, and were spent 2 days with us, and all of you that came in person. So I would like to thank the planning committee for organizing this meeting, and I will be remiss if I didn't thank Linda, Jessica, Ayana, Eric, and Kay for the support. We wouldn't be able to do this without them. So that's actually pretty clear. We'd like to actually thank our federal sponsors as well. And I would actually also like to remind you that the recording of the workshop will be available on the Chemical Sciences Roundtable website within a few weeks after the conclusion of the workshop. All of the attendants will get an email, so notifying them that this is going to be available for you. And also, somebody was asking me about this last night. There will be a written summary of the workshop. It's not a report, but it's a written summary of the workshop called the Proceedings in Brief. And I think the target date will be probably spring 2023, is that right? And so with that, I think I'd like to thank you once again and thank all the speakers. This has been a marvelous workshop and got excited. I'm a theoretical guy, but I'm ready to go to the lab and start doing some lab work. This is very, very good. And thank you so much for your attendance and see you next time.